Alright, good morning, calculus. It is Saturday morning, beginning of break. I told you guys I would get these videos up. So let's do this. Let's not waste any time. We are looking at number 14 in our manual. This is Rolles and mean value theorems. It's a little cut off there, but once again, thank you to Stu Schwartz from MasterMathMentor.com. He is the provider of a lot of this content. We're just working our way through it. Let's get started. Okay, so Rolles and mean value theorem. Let's just start with a little bit of kind of investigation here. So on the graph to the left, plot the point 2, 2, and 7, 2. So I'm going to plot those 2 points, 2, 2, and 7, 2. And then it says now draw 3 graphs of differentiable functions. Now that means that these differentiable functions have to be smooth and connected. That's what a differentiable function is. So just draw 3 differentiable functions that connect these 2 points. So let's do something simple. How about a blue one here? Let's do something maybe even more simple, just one turn in it, the red. And now let's go crazy. We're going to go up, and down, and up, and come back down. Okay, so we got multiple turns going on. We got blue, red, purple, all over the place. Is it possible that you can draw a graph for which there is not one point which the derivative is not 0? In other words, what it's asking here, derivative not 0, means can we draw a graph without horizontal tangents? That's what a derivative equals 0 implies. That's what it's saying. If there's a derivative equal to 0, then you have a horizontal tangent line, a flat slope, a 0 slope. Derivative equals 0. And why is that true? A lot of it is because, well, no, all of it is because that we start and finish at the same height. So if we start and finish at the same height, then we got to level out sometime in the middle. And he actually goes on later to note this, kind of like the what goes up must come back down. In other words, for this red line, what's going up must also come back down. For the blue one, we're going up and then coming back down. Then we're going down and coming back up. So it works both ways. If you're going to return, so here's the start, here's the finish, and the big idea is if we're going to return, in other words, returning to a value requires changing direction. And changing direction requires that we stop and then go the other way. So here's kind of the technical definition down here about Rolles theorem. Let f be continuous on the closed interval, so continuous from the endpoints, and differentiable in the middle and in between. And if your start equals your finish, then somewhere in the middle you have to have a derivative equal to 0. And that's the start of Rolles theorem. And here's where he mentioned it. In layman's terms, what goes up must come down, and what goes down must come back up. So if we're going to return requires, I won't even write that out. Return requires change in direction, and change in direction requires stopping, which is derivative equals 0. So let's do that. Let's see what's happening here. So now we're going to show that Rolles theorem works for this function here. So we got to sketch this graph. It's x squared minus 5x plus 6. It might help if we factor that. Sometimes factored form helps us a little bit. This would be x squared. Oh, not x squared. Let's take that back. And let's make this writing a little bit skinnier, easier to read. X minus 2 and x minus 3. That means that I have roots at 2 and 3. And if I'm to look at this graph, I would know that it comes down. It actually crosses here at 6. You know what? Let's make that even more accurate. We're going to cross at 6, come down to 2, and then we come down just barely below the line, and then we go back up, kind of like this. Actually, exactly like this. So that's kind of our parabola shape. It's probably even a little more vertically compressed. What are the x-intercepts? Oh, we kind of figured that out. That was natural for us to do there. They're x equals 2 and x equals 3. Is the curve continuous? Yes. Why? It's a polynomial. Polynomials are friendly. They're smooth, they're connected, and that's the same reason for over here. Yes, it's differentiable. It's a polynomial. That is the reason why. So you may now use Rolles' theorem to do so. Okay, in other words, it's saying it's continuous, check. Differentiable, check. The start equals the finish, check. Because f of 2 equals f of 3. They both equal 0. Then that means let's take the derivative and set it equal to 0 and find that place in between these two values. So in other words, f prime of x equals, well, if we're going to do that, it's 2x minus 5. That's a simple power rule, doing each term independently. And we know that this is going to equal 0. Somewhere, x is going to be between 2 and 3. Well, let's solve it. We add 5 to both sides. We got 5 equals 2x, divide by 2, divide by 2, x equals 5 halves, which is greater than 2 and less than 3. Check. It works. Okay, and this isn't exactly obvious, like, why do we need to be so particular and kind of be picky with this? It seems very detailed. The general idea is it's showing you that you don't always have to find that point in the middle, but sometimes you can clue into exactly where it is if you know a start and a finish. So let's go ahead and see what else we have coming here. Find all values, not just any, all values between the x-intercepts for which Rolles' theorem holds for the roots of this. So we got 3x squared minus x to the fourth. Where are the x-intercepts? Well, it'd be helpful if we factored that. Let's do that. Let's start there. So we can pull out an x squared. And so there's that factor, x squared, but then we'd have 3 minus x squared left over. And this would factor. I know it's not exactly obvious, but it is a difference of squares. It would be square root of 3 plus x and square root of 3 minus x. And then we'd have x squared out here as well. So from this point, we would see that we have x-intercepts. If we set this equal to 0, we can find our x-intercepts. We know that x equals 0. We also know that x equals plus or minus square root of 3. So that means that, you know, if I'm looking at this like on a number line, we have negative square root of 3, 0, and then we have square root of 3. That means somewhere here in the middle on the left side, and somewhere here in the middle on the right side, that the f prime is going to equal 0. Why? Because there's an average change. In other words, the change between 3 and 0, what's the slope? Slope equals 0, the average. So the average slope equals 0. That means that the derivative, the instant slope, is also going to equal 0. That's an interesting idea here. Let's go ahead and work this out. So first we need to find f prime. F prime of x. It's a pretty simple derivative. Again, power rule. So we got 6x minus 4x cubed. Now if we were to factor this, that means we have f prime of x equals, we can pull out a 2 and an x. Then we have 3 minus, what do we have here? 2x squared? 2x squared. So now that's kind of interesting. As I'm looking at this, I find that x equals 0 is actually a location for us to have a 0 in there as well. So we're going to have 3 answers. So we were guaranteed 2. This blue and this red zone guaranteed us 2 solutions. But now I'm looking at, we're going to find 3 because we get 1 here from the first part. But then the other piece here, 3 minus 2x squared, if I'm to set that equal to 0 and solve, then I got 3 equals 2x squared divided by 2 divided by 2. Square root of 3 halves is going to equal x. And that's plus or minus because we're taking a square root. So we got 3 answers. There's 1 and then 2 and 3. Cool. And it says confirm using your calculator. You know, I'll let you guys kind of work that one out in detail, but just to kind of show you what we would do, we'd plot it and then find those 0 slopes. So let's open this up, but let's do y equals, we want to clear this old function out of there. Let's make this bigger for you guys to see. Alright, we're typing in, what's the original graph? It was 3x squared, 3x squared minus x to the 4th. Now for our window, I'm just going to go to standard, so zoom standard, zoom 6. Alright, and that does look kind of true. I'm going to zoom in just to make sure. So I'm going to zoom into, let's see, about 3 to -3 in both the x and y. So -3 to 3. You know what, for the y's, let's go -1 to 4, or -1 to 5. Just go a little bit higher there. Let's see what we got. Okay, so we have something going on here for a 0 slope between square root of 3 and 0. And then at 0, even though we hit 0, we also have a 0 slope there. So we have definitely these 2 places in between, though. That one in the middle is kind of just extra. So how could I figure out when that hits a maximum there? That's actually something I can calculate on a calculator. So I'm going to do second calc. I'm going to calculate this maximum, which is number 4. Left bound. Well, let's do it between square root of 3 and 0. So I could actually type that in. Or we could just, what's this value here? That's going to be 2. So -2 for my left bound. And not 0, but how about 0.5? No, -0.5. Whoops. Clear that. Second, calculate maximum, which is 4. So we want to do it, well, we can do it on this side. How about that? 0.5 and 2. Where's the guess? Somewhere in between there. Oh, that's too far. Let's go back into the middle. I think it's about here. So that's going to be x equals 1.22. And if I were to calculate what's the square root of 3 halves, I think that's what I would find. So let's go ahead and figure that out. So square root second squared is the square root, and then 3 divided by 2 should be the same answer. I think it was about 1.55, 1.22. Maybe that's what it was. I don't remember. You guys probably do, but that's what we should have gotten. Alright, so let's move on to another one. So this works, and it does confirm it worked with our calculator. This is different. You know, it's applying our knowledge here, but it's almost like we don't really seem to have much information. But this is a good transition to the second half, which is kind of how we're going to use Rolles' theorem, but in a more general way. So you're driving in a car, traveling 50 miles an hour. Okay, so our rate, or our slope at the start, is equal to 50 miles an hour. Cool. And then we pass a second police car, but that's 4 minutes later. We pass a second police car, and so 4 minutes later, we're still driving 50 miles per hour. But the catch is the second police car is going to nail us for speeding. So we're speeding here, and it says the distance between the 2 cars was 5 miles. So how can he prove that you were speeding? So I started at 50, I ended at 50, but the only way that I was speeding is if I was speeding somewhere in the middle. So how would the cop even try to calculate my overall speed? Well, the information he has is 4 minutes in between and 5 miles. Well, let's look at that. If we have 5 miles over 4 minutes, that would give us our speed. And that's 1.25 miles a minute, you could say. But this is kind of interesting because 4 minutes, we need to convert this to hours. So I'm going to do a little unit conversion here. I know that there's 60 minutes in 1 hour. And what's happening here is this is really 1 over 1 because 60 minutes and 1 hour are equal. And then I can say the minutes, those simplify to 1 over 1. 60 over 4, I could simplify that to 1 and 15. And then that means if I multiply this out, I get 75 miles per hour. That is speeding. Yes, it is. So my average speed equals 75 miles per hour. And here's the catch. Here's an even bigger deal. Like if my average speed was 75 miles per hour and I started at 50 and ended at 50, I had to go even over 75 miles per hour, somewhere in the middle, at least for a little bit. That was pretty fast there, but man. So yeah, my average speed was 75 miles per hour. There's no way that I could have stayed under the speed limit and still made an average speed of 75 miles per hour. So this is why, right there. Good job, cops. And here's visualized what is happening. So the idea is that not only if your start equals finish, but look at this slope here. This is our average slope. Our average slope, our average rate. Because we're just finding the slope from one point to another. This is old school algebra. This is not calculus. This is algebra, finding the slope between 2 points. But now we know if we have continuous curves and differential curves, I should say, in between those 2 points, that average slope has somewhere in the middle where these two slopes are actually parallel or the same, in other words. So these two slopes are the same. In other words, the derivative, this tangential slope, is equal to the average slope. So the instant, this is the big idea, the instant is going to equal the average. And that's what's happening here. The derivative of the instant is going to equal the average slope. That's an average slope. This is old school slope formula. It's in function form, but if you think about it, it's the same as like the difference in y's over the difference in x's. Same exact thing. Well, how can we apply that? Let's see what's happening here. Given this function, find the value c. So we're going to find that part in the middle between 1 and 5. Well, here's the value at 1. Here's the value at 5. That satisfies the mean value theorem. So mean value theorem basically says the instant, or the derivative, f prime of c is going to equal our average slope, which is just, old school slope formula. F of b minus f of a over b minus a. So let's figure out what those values would be. Now, I could do this visually pretty easily. I'm going to do it algebraically as well. But let's just show you visually what's happening. So we're looking for the slope of this line between these 2 points. So that would be a rise over run kind of calculation. So we're going up here, and we're going to run this much. And these algebraically represent this distance here. This is f of b. No, that's not f of b. Pardon me. Take that back. This is b minus a. That's our run. And our rise here, this is f of b minus f of a. That's our rise. So how much do we rise? From -2 to 2, that's going to be 4. And how much did we run? That's from 1 to 5. That's also 4. So this is actually a pretty simple slope. It's just 1. So let's do that algebraically, officially here, we should get a slope of 1. If we're trying to find f of b minus f of a over b minus a. This is our average slope. And f of, what's the first point, or the second point? F of 5. It's going to be f of 5 minus f of 1 over 5 minus 1. The 5 minus 1, that's easy to get, that's 4. But what's f of 5? F of 5 is going to be 3 minus, what do we got? 5 over 5, which is 3 minus 1, that's 2. So up top, this is a 2. Then what would be 3 minus 5 over x? This is going to be 3 minus 5 over 1. 3 minus 5 is negative 2. So it's going to be 2 minus negative 2, which does add up to 4. So we get the same result algebraically. I just want to show you that, let's say you couldn't draw a picture. Can we still do the algebra? Yes. And it equals 1. The average slope equals 1. So then the key that I'm looking for is to find a slope somewhere in between that's going to be about that. Looks like maybe about here. Somewhere around there. So, actually, let's do this a different way. I have a better idea. Take this back. I'm going to draw a line between these 2 points. There's my average slope of 1, or at least close to it. So then I'm trying to find somewhere. Oops. I want the line. There we go. I'm going to find somewhere where the tangent equals that. And it looks like it's right about there. Somewhere about here is where these 2 lines would be parallel, where the 2 slopes would be the same. So I know the slope has to equal 1. How could I find that instant slope? I want to find the instant slope, or the instant rate of change, equals 1. Well, that's when f prime of x, or f prime of c, I guess you could say, is equal to 1. Well, let's figure out what the derivative is, and then figure out when it equals 1. So f prime of x, let's see, what do we have here? 3 minus 5 over x. If it's 3 minus 5 over x, that's the same as 3 minus 5x to the negative 1. So the derivative, the 3 is going to go to 0. Then we're going to have negative 1, drop that negative 1, times negative 5 times x to the negative 2, which would simplify to 5 over x squared. And so this is our derivative. That's the function derivative. But we want to have this equal 1. Now we can do some algebra and actually figure out that value. I'm going to multiply both sides by x squared. And I know that x squared is not 0. X does not equal 0, so this is okay to kind of get rid of it in this way. Because, how do I know that? Because x is between 1 and 5. Okay, so we got rid of this. On the left side, we have 5 equals x squared. And when we square root, x equals square root of 5. Now, a lot of times we say plus or minus, but in this case, we only want the plus. Why? Because this is where that's going to be. So what's this point right here? This point is square root of 5. That's interesting. What did we find? We found that the average equaled the instant. The question is, where? We just found that. We answered the question. All right, let's look at the next one here. Find the equation of the tangent line to the graph of this on that interval at the point which is the solution to the mean value theorem confirmed by calculator. Okay, so here's our interval, here's our a, here's our b. We got to figure out what the slope is. We got to figure out what the average slope is. That's going to equal some number. And then we got to set that equal to the instant slope, which is the derivative. And then answer the question, where is this true? Where does this happen? That's the big idea. All right. Well, the average slope, that's going to be f of b minus f of a over b minus a. Let's figure that out. That's going to be f of pi is equal to 2 times pi plus sine of pi plus 1. Well, sine of pi is 0. So this is really just 2 pi plus 1. F of 0 is going to be 2 times 0 plus sine of 0, which is also 0, plus 1. Well, 2 times 0 is 0. Sine of 0 is 0. So that just leaves us with plus 1. So f of 0 equals 1. So if we are trying to calculate f of f of pi minus f of 0 all over pi minus 0, that's going to be 2 times pi plus 1 minus 1 over pi minus 0. Plus 1 minus 1 are going to cancel each other out. That gives us 2 pi over pi, or even more simply, just 2. So that's our number in the middle. This is our number that we're going to put in the middle. 2 is going to be the number. That's what our average slope equals. So we got to set that equal to the instant slope and then answer the question, where does this happen? Well, we need to find the derivative then. Well, let's find f prime of x. Let's do this in red. F prime of x is going to be, we got a simple constant multiple rule here in the first part, so that's a 2, plus sine of x. The derivative of sine is cosine. And then the 1 goes to 0. Okay, that's not too bad. Is that all we're doing? It seems a little bit interesting. Oh, okay, I got you. So that's our derivative. What does this have to equal? It has to equal that average slope, which in this case was 2. Now we're plugging it in. So now we got to solve this equation for x. What does x equal? So I subtract 2 from both sides. Cosine of x equals 0. When is that true? Well, in the interval between 0 is less than x is less than pi. So if you're to think about your unit circle, you're here in that first half of the rotation. When does cosine equal 0? Right here in the middle, at pi over 2. So x equals pi over 2. That's the where. Done. Confirmed by calculator. Oh, okay, so we got to plug this into our calculator just to make sure. So I'm going to go plug in the function here. This function is 2x plus sine x plus 1. Oh, we got to close off that sine of x. Plus 1. All right, let's graph. Oh, and by the way, we're looking between 0 and pi. This is 0 to 3. So let's just go from 0 to pi. So if I go to my window, it's going to be from 0 to not 3, but about 3.14. I can be more exact, at least more accurate, by just typing in pi. And let's go from y scale -1 to 5. I guess that's fine. Let's see what we got. Okay, so this is kind of our graph. It looks like we're even going higher. So if we're going from 0 to pi, we need to go even further. So for my y value, let's go from -1 or 0. How about 0? Not 0 to 0. This is 0. We'll go from 0 to 10. What does that give us? Alright, so we are starting to level off there a little bit. And we're trying to make a tangent line, so we're going from here, from 0 to pi, and that's a slope of 2 apparently. And then somewhere here in the middle, actually at pi over 2, so right in the middle, perfectly in the middle, it balances right at that level. So let's, I'm going to show you this visually. Let's drag this over into our slide. So what do we mean by this? Just to give you a little bit of visual representation. I'm going to shrink this down a little bit. What we're saying is that the slope from here to here, this average slope equals 2. And then if I were to duplicate that piece, so I'm going to duplicate it here. There we go. So that's the same slope, and somewhere here in the middle we come up with another location where it has the same exact slope. It's right there, which is at x equals pi over 2. So we got parallel slopes. Same slope. Alright, soak that in. Let's finish it off here. Why can't we use mean value theorem on this interval? Well, there's only 2 requirements. The 2 requirements are continuous and differentiable. Well, is this function continuous? Yeah, it should be. Let's draw a graph and let's take a picture of it, or let's see what's happening with the graph. Maybe that'll make it a little more obvious. We're looking at the interval -1 to 1, so we'll keep that in mind as well. This is going to be x to the 2/3. We don't need that 1 there. And for our window, we're just looking from -1 to 1. I don't really know what our y values need to be. Let's see what we have so far. Okay, so we can shrink down probably just from 0 to 2 for our y values. Let's see what happens. Ooh, that's interesting. Let's drag this over and talk about it. So right here, there's a problem. We're not differentiable. Not differentiable. Why? Because it's a sharp turn. Now, that's visually what's happening. But could we have figured that out algebraically? Actually, you can. And to know that something's not differentiable means that the derivative does not exist on or at a certain point. At x equals some value a or c or b or whatever you want to call it. So let's take the derivative and confirm that. Let's look at it. If we were to find f prime of x, that would be 2/3 x to the -1/3, which would simplify to 2 over 3 times the cubed root of x. Okay, here's the problem. X cannot equal 0, which we're seeing here as well. X cannot equal 0, because if we put in a 0 there, that's a 0 in the denominator, that's undefined, therefore the derivative is undefined at that point, and we can't use it. And the whole key to this question is that we have to do it over this interval. We can't do it from -1 to 1. In fact, if we did it from 0 to any number, positive, or any negative number, negative, to 0, it's okay. But if we include 0 in the interval, where we go negative number to a positive number, where 0 is in the middle of our interval, not okay, because it's not differentiable. Okay, so that's the big idea. All right, that's the end of this one. Watch it again and again and again and again until it makes sense, because repetition is good for you. Calculus is good for your brain. Bye.